So in this example, I just want to show you how you can use differentiation and integration to come up with power series representations for some pretty complicated looking functions. So here is my f of x, right? Super ugly looking. And I'm going to say that we can come up with, right, a kind of easy-ish description, a series description that will approximate this not so nice function. So we're going to remember a few things. So here's our little recall. We know that 1 over 1 minus x can be represented as the series x to the n equals 0 to infinity for, right, the x is less than 1. And that we know that we can integrate a series with respect to, so we're integrating this series with respect to x, and then what we get then is, right, the antiderivative, just like we do, right, so power series, and then you can have a constant, and we can also differentiate. So if we take the derivative with respect to x of a series, then we can use the power rule for that as well. So sum n x to the n minus 1. And for that one, we just go ahead and start at 1. Otherwise, we have a 0 term, and it doesn't make sense. Okay, well, it doesn't matter. It makes sense, it just doesn't matter. Okay, so we're going to use these three things, and we are going to come up with a power series representation of this bad boy here. Okay, so, right, you're looking for some sort of either integration or differentiation rule. And what we're actually going to do is we're going to do it one way, and then we're going to undo it, okay? So you might notice here that, right, if you set u equal to this 1 plus x cubed, du is kind of staring at us up here, right? So that kind of makes you think, well, geez, what if I integrate this? What would that look like? Okay, so let's see. Let's see what that looks like. So we're going to integrate negative 3x squared over 1 plus x cubed squared, okay, with respect to x. What is that going to give us? All right, so we'll do a quick little u sub. So du will be 3x squared dx, which I have, except it's got a negative, so we'll just move that negative sign out front. So we're going to integrate, I've got u to the negative 2 negative, u to the negative 2 du. I know you're thinking, well, why are we doing this? So, oh, don't worry, it's going to, okay, you can worry a little bit, but it's going to be clear here in just a second. Okay, so we're going to get negative u, negative 1 divided by negative 1. So I can get rid of the negative signs, yay. So I have 1 over u. Ready? 1 over, what was u again? Oh yeah, 1 plus x cubed. Okay, so if we integrate the function we started with, we get to this, right? 1 over 1 plus x cubed. So we're going to look at that, 1 over 1 plus x cubed, and we're going to rewrite it, right, in our geometric series form. So we have to do a little bit of, right, manipulating here because it's not, right, the key parts, remember, it's the, right, 1 or you factor it out. It's the 1 on the bottom or you factor it out. And it's supposed to be a minus. It's not that. So I've got the two ones, but I need to make that a minus. Oh, and then I need to do something there. So this will be 1 over 1 minus negative x cubed. Okay, so now, right, my integral, my antiderivative, right, oh, sorry, plus c, but I'm going to get rid of the plus c here in just a second. So my antiderivative matches pretty darn closely with my geometric series. So I can write this rational function. I can write this rational function, which was the antiderivative, as this power series. Okay? So right now I'm going this way. So this is equal to the sum 0 to infinity of x, which is now being played by negative x cubed to the n. Okay? So what we just found is a series for the integral of our original function. Right? So this is a series that represents the integral of our original function. So if I want a series for the original function, okay, so this, let me write that down because that's a lot to keep in your head. So this is a series for the integral of the original function. So if I want a series for the original function, right, we went one way. So now we have to undo what we just did to get back to the original. So we're going to differentiate to get back. Okay, and how do we differentiate that? Well, let's see. Powers to powers, I can multiply. I'm going to do a little manipulating and take that -1 to the n out. So my series, if I rewrite that series there, so n 0 to infinity, -1 to the n, x to the 3n. Okay. So we'll take the derivative with respect to x. So that's going to be, and it's going to stay the series, right? So n 0 to infinity. I'm going to have my -1 to the n still. And then I will have a 3 times n, x to the 3n minus 1. So that plus c that I didn't bother writing until the end, it's like, oh yeah, I need a plus c. The reason why I doesn't matter is that once we take the derivative to get back, the derivative of that constant would be 0. So it goes away. Do I keep my 0 here? No, that's going to 0 it out. So you can start at 0. It doesn't matter. It zeroes it out. Most people are going to start at 1. So that is what's going to go in that box up top. I'm going to slide and I'm going to copy it in to the answer box. So this is going to be equal to -1 to the n times 3n times x to the 3n minus 1.